In intro stats, we focus on using the chi-square goodness of fit test with a categorical variable that reflects different groups in our population. As a statistical test, it's pretty simple and straightforward, and for intro stats, that's great. But one of the very cool things about the chi-square goodness of fit test is that it's also widely used in more sophisticated, advanced statistical analyses that go far beyond what we cover in intro stats. In this video, I'm going to talk about this at a conceptual, non-mathematical level, so you can see the potential power it holds, so that you can be a little better informed if you read an article that talks about using a chi-square goodness of fit test in a different way than we learn in intro stats. Now, as I said, in intro stats, when we learn the chi-square goodness of fit test, it's based on a categorical variable that reflects different groups in our population. Our null hypothesis is based on each group reflecting a specific proportion of the population, 10%, 20%, 30%, something like that, right? And our alternative hypothesis is based on at least some of those groups not actually reflecting those proportions. Like other statistical tests, right? We researchers are interested in the alternative hypothesis. In this case, we think the actual proportions in the population are different than those specified values from the null hypothesis, and we want to reject the null hypothesis. And again, let me be perfectly clear, for intro stats, that's exactly what we're doing, right? But this is actually where things get very exciting in advanced stats. Because in some advanced statistical approaches, there are variations of the chi-square goodness of fit test where you don't want to reject the null hypothesis.
That's crazy talk!
That's not crazy talk.
That's right. It's actually not that crazy. Let me explain why. A common situation where you see this come up is in model testing. In advanced techniques such as structural equation modeling, you may propose a complex model in which some variables influence other variables which influence other variables. These models can help us understand more complex processes of how things work. For example, here's a model from a study I did with Milena Wiggin, Christy Yoshinagi-Tano, and other colleagues, in which we examined how family characteristics and newborn screening and early intervention all influence language development in children with hearing loss. And if you look at a model like this and think about it for a while, you may recognize that kind of based on this model, you might expect to see, notice my language here, you might expect to see certain associations between the variables. For example, let's do a simple one. If you have a model with 3 variables, A, B, and C, and you think that A causes B and B causes C, then you would expect the correlation between A and B to be larger than the correlation between A and C, because A and B are closer together in that chain of effects than A and C are. Now, if you don't see why that's the case, don't worry. We're only interested in this at a conceptual level here. If you want to know why, take my structural equation modeling course. For now, you can just take my word that based on our model, we can expect to see certain associations between variables. stronger correlations or covariance between some variables and weaker correlations or covariances between other variables. In fact, based on the model like this and patterns that you actually then see in the data, we can go further and estimate specific values that we expect to see for correlations and covariances between our variables, if this model is true. Again, notice my language here as well. We can create a list of expected correlations and covariance values that we expect to see if the model is true. This sounds a lot like the null hypothesis in a chi-square goodness of fit test, doesn't it? And it is our null hypothesis when we use the goodness of fit test for model testing. We're just framing our hypotheses, both the null and alternative, a little differently. Instead of expected number of people in groups, we're looking at expected values for correlations and covariances. So our null hypothesis is that the correlations or covariances in the population are consistent with the values we expect based on our model. And the alternative hypothesis is that the correlations or covariances in the population are not consistent with the values that we expect to see based on our model. And notice that instead of framing our hypotheses based on if the null is true, we frame them based on if our model is true. But otherwise, it's the same idea. We then literally do a chi-square goodness of fit test, comparing the observed values for those correlations and covariances with the expected values if the model is true. We calculate our chi-square, we find our p-value, we make the decision to reject or fail to reject our model, which again is functionally the null hypothesis. Pretty slick, isn't it? But notice the twist. We've actually turned hypothesis testing on its head. Remember, in hypothesis testing, we're interested in the alternative hypothesis. We want to reject the null hypothesis. But in this case, I'm obviously interested in my model. I want the data to support my model. But my model is the null hypothesis. I don't want to reject my model. I don't want to reject the null. I know. This goes against every instinct we have learned so far with hypothesis testing. But for this specific situation, our instinct is wrong.
If every instinct you have is wrong, then the opposite would have to be right.
Yes. I will do the opposite. I used to sit here and do nothing and regret it for the rest of the day. So now I will do the opposite and I will do something.
Yes, this is the opposite of what we've wanted so far. But when we do a chi-square goodness of fit test for model testing, we don't want to reject the null. Think of it this way. I'm proposing a model and a non-significant chi-square indicates that the correlations or covariances in the population are consistent with what I would expect to see if my model is true. A non-significant chi-square supports my model. I want to keep the null hypothesis and not have to reject my model. In contrast, a significant chi-square suggests that the correlations and covariances in the population are inconsistent with what I would expect to see based on my model. My model doesn't reflect reality. The alternative hypothesis and a significant chi-square means I have to reject my model. Ouch! We talk about this as the model not fitting the data. Now, there are all sorts of implications to this that go beyond what we cover in an intro stats course. And again, we won't worry about that here. For example, there are situations where you may be testing someone else's model and you actually do want to reject their model, right? In fact, you can use the chi-square goodness of fit test to compare your model to someone else's model to see which model best fits the data, which model best fits reality. Oh, pretty cool. I mean, you can compare your theory with her theory with his theory to see which seems strongest. That's an incredibly powerful use of what, at first glance, seems to be a fairly simple statistical test. All right. So with that, let's wrap up this discussion regarding the chi-square goodness of fit test for model testing. Again, this is something that you'll learn in more advanced stats courses, but it's good to have some understanding at a conceptual level because you may come across it when you're reading research articles. Okay? Take care. Bye-bye.
So now I will do the opposite, and I will do something. Excuse me, I couldn't help but notice that you were looking in my direction.
Oh, yes, I was. You just ordered the same exact lunch as me.
My name is George. I'm unemployed and I live with my parents.
I'm Victoria. Hi.